Richard Feynman's call for quantum computation in 1981 has led to rapid scientific developments in different potential architectures. In 2000, David DiVincenzo defined 5 criteria he thought were essential to creating an effective quantum computer. Research into electrons on liquid helium began because there are several different ways to define a discrete qubit. Each single electron could be the well-defined qubit. Since these electrons naturally exist in extensive arrays above the liquid helium, this architecture is more scalable than other promising structures. The magnetic purity and low temperature of the liquid helium environment also hold promise in creating long coherence times for quantum measurements of these qubits. Most research in quantum computing architectures has focused on the 5 primary DiVincenzo criteria. There are, however, 2 more important criteria that go into making an actual quantum machine operate. Devices need to be able to generate so-called flying qubits and transmit them in order to transfer information. Recent research by Brad Berry and the Lion Lab at Princeton have shown that liquid helium is an exceptional transmission medium for electrons. These ultra-fast electrons would carry the information in a future quantum device. The most promising application of electrons on liquid helium could in fact be providing a network of transmission for different types of qubits because of this architecture's remarkable reliability in transmitting signals. Liquid helium forms when a reservoir of gas is cooled to very low temperatures. At 2.17 Kelvin, the helium atoms undergo Bose-Einstein condensation and form a superfluid. The helium superfluid is chemically inert. It only interacts with electrons above it through dipolar interactions. These weakly attractive forces create a potential well above the helium layer. The electronic wave function maxima are only a few nanometers above the liquid. Energetically above the 2-dimensional electron gas is a state with a spatially varying wave function. The upper structure is a crystalline structure effectively made of only electrons. This so-called Wigner's crystal and the 2D electron gas below it have both been used in quantum engineering applications. The electrons in these layers can be used as qubits if properly controlled, as generators of entanglement, or as a transmission media for other qubits. In 1999, Platzman and Dykman proposed that electrons on superfluid helium could be a structure suitable for quantum computing. The 2 theorists realized that the electronic wave functions situated near the surface of the liquid helium are essentially hydrogenic states, governed by a Coulomb potential. These states are coupled to surface waves called Riplons. Microwave fields can control this coupling, resulting in Rabi oscillations, which transition the electrons between the first and second hydrogenic states. The Rabi frequency is only a nanosecond, which allows for over 10,000 oscillations between these states in one relaxation time interval. As a result of these properties, Platzman and Dykman proposed that the first and second hydrogenic states in this 2D electron gas can act as qubits. These electrons can easily be singled out. At low temperatures, Coulomb interaction dominates any kinetic motion, and the electrons will strongly stabilize to a 2-dimensional lattice. The next step is to apply a grid of electrodes with the same spacing as the natural lattice. Now each electron in the system is available for manipulation by an externally applied voltage. We can apply this voltage by incorporating a capacitor into the overall device. The filament shown in the diagram generates the free electrons from the fluid medium. Then, these electrons form a 2-dimensional electron gas above the liquid helium layer. The capacitance lets us apply a fixed voltage to a given electron bit. This voltage determines the resonant frequency a microwave field would need to be in order to excite the bit from the ground state, m equals to 1, and the excited state, m equals to 2. The next question to ask about this system is how we could read out information related to these qubits. The answer is actually quite simple. We can learn about these states by taking advantage of quantum tunneling. Coulomb potential tunneling is well studied. All we need to do is apply a reverse bias electric field across the capacitor from the previous image. Then we tune this field to the value where only the excited electron will tunnel out of the barrier. To catch this electron, we need to set up a charge-coupled imaging plate with high spatial resolution. The electron will hit a given spot and record a data point. As we repeat the cycle of microwave initialization, time delay, and then reverse field application, this imaging plate will eventually give us a picture of the wave function of the excited electron. Platzmann and Dykman devised a scheme to implement these protocols, where voltage noise, radiative emission, and non-radiative decay were negligible. These factors would lead to high accuracy and coherence. The theorists concluded their publication by saying that no technological barriers were apparent for this technology. Indeed, the next year, researchers at the University of London were able to fabricate the device they had proposed in the form of a Wigmer crystal. This material behaved as a set of 1-electron wires. These wires were made by pouring liquid helium into etchings made on a semiconductor substrate. However, the structure had unanticipated nonlinear effects and began to disintegrate with high-frequency signals. After these discoveries, researchers began to look into new ways of creating qubits from the liquid helium architecture, while still taking advantage of coherence and scalability properties. There are now several accepted ways to implement quantum information processing with liquid helium electrons. Lyon discovered that the methods of electrostatically controlling spin qubits in semiconductor 2D electron gases are also applicable to the liquid helium electron layer. In fact, the spin qubits in helium have coherence times that could reach up to 100 seconds. Zhang and Wei recently theorized a way to entangle the spins of two distant electrons by using their vibrational energy. These researchers implemented these experiments by controlling their devices with 3 different magnetic fields. Creating usable qubits out of liquid helium may be many years in the future, but experimentalists in the past 5 years have pioneered a more promising application of this architecture in the form of quantum information transmission. Forrest Bradbury pioneered this idea as a PhD student in the Lyon lab. In 2011, the group demonstrated record-fast electron transmission with an unprecedentedly low fail rate. Over 1 billion transmission cycles could run without the loss of a single electron using their device. This image represents 3 of the 120 parallel channels in the Bradbury device for rapid and accurate electron transport. This side cross-section shows the silicon dioxide layer, used for shielding the gates from one another. In this image, the dark gray represents the electron layer floating on the liquid helium. The light gray represents the metal interconnections in the device. The line patterns in this image represent gates. A set of 3 gates, known as the clocking voltages, are voltages 1, 2, and 3. Each of these 3 gates defines one CCD, or charge-coupled device. This is called a pixel. For example, these 3 represent a pixel, these 3 are another pixel, etc. Bradbury and his team found that electron transmission was possible in this device once the clocking voltage was increased past 3 volts DC. The electrons in this device flow from the right reservoir to the left reservoir, then back around through the device to the right reservoir again. All gates in this device are connected to the pixel system, except those to the far right of the right reservoir. This is the control and measurement part of the apparatus. The sense, twiddle, and door gates mediate the transport of the electrons. The sense gate acts as a non-destructive detection mechanism. It is controlled by an AC voltage applied at the adjacent twiddle gate. The door gate acts as a transmission regulator. As one electron passes between the right and left parts of this schematic, it appears as about 1/20th of an electric charge on the sense gate. Properly transferred electrons will end up at the same pixel they started on. Repeating this detection scheme over many cycles allows measurements to verify if the electron was lost or not. This CCD approach is how Bradbury and his team were able to quantify their extremely low fail rate. This was an experimental demonstration of the reliability of the Bradbury device. This trial had an average of 0.75 electrons in the channels, and this one had about 4 in each channel. The matching of this number of electrons in the wire at every pixel across the device indicates the high fidelity in electron transfer. Bradbury's result, combined with the extremely high mobility of the 2D electron gas, is very promising for transferring electrons in space. Whether or not superfluid helium ever becomes a widely used qubit architecture, This structure could be an answer to communication between qubits, de Vincenzo's last requirement.